Hello and welcome to this video in which we will compute the Fourier transform of a rectangular pulse. This is a useful example for two reasons. First, it shows how to compute the Fourier transform using the integral definition of the Fourier transform, and this is a problem where the math involved remains easy and fairly tractable. You may not think about it that way halfway through, but it's not that bad. And second, the Fourier transform of a rectangular pulse has many important applications in Fourier analysis, and we'll look at two of these applications at the end of the video. So I've drawn a rectangular pulse. You can see that it has amplitude 1 between values of t going from -a to a, and it has amplitude 0 everywhere else. Sometimes you'll see this denoted as p of t, or sometimes you'll see it denoted as p sub a of t, where the a shows the duration of the pulse. So let's begin by writing down the integral definition of the Fourier transform, which is this. Now, at the risk of being potentially confusing, but hopefully making it clear what we're going to do when we compute this integral, notice that the variable of integration here is t, and that omega, in terms of how we treat the integral, is just a constant. So that when we finish our integral, we will have integrated out the t's, but the omegas will still be there, and that's how the Fourier transform x of omega becomes a function of omega, is that we integrate out the t's, leaving just the omegas. The integrand here is an easy function to integrate for the following reason. If you look at values of t between -a and a, so between here and here, the function has a value of 1. Okay, so I can actually just write this as 1 times e to the minus j omega t. And then for values of t greater than a, it's 0. So the integral from a to infinity of this whole integrand will be 0, so I can ignore it basically. That means that my upper limit here will be a. And for values of t less than negative a, x of t is 0, which means that the integrand from -infinity to negative a will also be 0. So I can write this whole integral as the integral from negative a to a, 1 times e to the minus j omega t dt. Okay, and to make things a little easier, since we're multiplying by 1 here, we'll just cross that out. We don't want it to get in the way. Okay, so now I can work this integral. I'm just integrating an exponential over a finite range. This is a fairly straightforward integral. So I have 1 over negative j omega. That's this constant out here in front of the t in the exponential. And then I will evaluate this e to the minus j omega t going from negative a to a. Now I want to evaluate this at the limits, and I get 1 over negative j omega. I replace t by a in the upper one, in the upper limit. I get e to the minus j omega a. Then I subtract e to the minus j omega negative a. Now we can do a little bit of just manipulating the algebra here. This negative sign cancels this negative sign, and this negative sign here I can get rid of by putting a negative sign here and a positive sign here. I end up with 1 over j omega e to the j omega a minus e to the minus j omega a. These next several steps may look like I am just randomly choosing numbers and multiplying and dividing by them, but there is method to this madness. The idea is that I know what I want the final solution to look like, and I know how to get there having seen other people do it. So if you're looking at this and saying, why on earth is he doing this? Hang on. In a little bit it will become clear why we're doing it. So now I multiply the top and bottom by 2, and this is equal to 2 over omega 1 over 2j, here we go, e to the j omega a minus e to the minus j omega a. Okay, so you look at that and you immediately say to yourself, that looks like Euler's formula for a sine. And in fact, you would be right. If you don't immediately say that, then don't worry. It's one of those things that if you do this for a while, it just sort of sticks in your head. So this part here is equal to sine omega a. Isn't that great? The whole thing just works out so beautifully. And so the last thing I will do here is multiply top and bottom by a. And again, this is something we do because we know what we want to end up with. And I will write this as 2a, and then I'll take my omega a here. So I have 2a times sine omega a over omega a. A pattern like sine of omega a over omega a occurs often enough that it has its own name. We call this sinc of omega a. In general, sinc of x is the sine of x over x. Okay, so we can write this whole thing as 2a times the sinc of omega a. You'll notice that it's possible for x to be 0. In fact, x can go to 0 in a lot of situations, in which case I have sine of x over x, and since sine of x is 0 and x is 0, I can actually look at the limit as x approaches 0, and that limit is 1. So let's go to MATLAB, or your favorite MATLAB equivalent, and plot the sinc function. Well, let's start off by saying a is equal to 2. Seems like a good number for a. We'll create an omega. And we'll have omega go from -10 with an increment of 0.1 up to a final value of 10. We'll choose s to represent the sinc function and compute it as sine a times omega divided by a times omega. And now we'll plot s as a function of omega. So this plots the sinc function as a function of omega. You'll notice that it goes up to a value of 1 at omega equals 0, and it has a value of 0 everywhere that the sine function is 0 except for omega is equal to 0. So it's 0 when the argument is an integer multiple of pi. Now, in our case, because the argument of the sinc function is a times omega, and a is 2, we get zeros whenever omega is an integer multiple of pi over 2. So, at the beginning of the video, I told you that we would give a few examples of where the Fourier transform pair of the rectangular pulse and the sinc function are used in real life. One of these is windowing, and the idea behind windowing is this. Imagine that we start looking at a signal, say s of t, at a given time, say right here, and stop looking at it. So we're looking at it, recording it maybe, and stop looking at it after a certain amount of time. This is called windowing, and it's done all the time in real applications such as speech and music coding. Mathematically, this process of windowing is equivalent to multiplying our signal s of t by a shifted rectangular pulse p of t of the appropriate width. The spectrum of p of t, that is the Fourier transform of p of omega, will affect strongly the spectrum of this windowed signal, this guy here. And so choosing a proper window is a very important thing in many signal processing applications. For our second application, imagine that we have a filter that cuts off frequencies above some value of omega c. So it has a frequency response that looks something like this. This is omega. This would be the response of the filter, and it might look like this. Okay, this is called an ideal low-pass filter and shows up in a lot of different theoretical applications. Now, this is a rectangular pulse in the frequency domain. You'll notice here that the axis is frequency. Due to a property of Fourier transforms called duality, if I have something that's a rectangular pulse in the frequency domain, in the time domain, it will be a sinc function. So it looks like this. So the idea is that for a low-pass filter, this h of t represents an impulse response, which has some fairly interesting implications about ideal filters. One is that they don't actually exist in the real world. But this also illustrates the principle of duality. So having figured out this guy, that is the Fourier transform of p of t, and discovered that it's a sinc function, it's fairly easy to discover that the Fourier transform of a sinc function is a rectangular function. So that's the second example. This pretty much concludes this video, and thanks for watching.